what I'd like to talk to you guys today about is some of the work we did in 2015 looking at some of these small stars that may potentially build up abiotic oxygen in their atmospheres. And I want to take a couple slides and actually talk about Proxima Centauri b. So just to orient everyone with the big picture, I'm going to bash on M dwarfs for a while. So not an exhaustive list of the pros and cons, but potentially M dwarfs have very long main sequence lifetimes. They have very stable habitable zones over long periods of time, which is great for evolving life. They are also the most abundant star type, and they are more likely to have rocky planets, as some of Ravi's work pointed out looking at occurrence rates for M dwarfs. On the con side, they have very long superluminous pre-main sequence lifetimes, which could potentially dehydrate planets or turn gas giants into terrestrial planets, as some of Rodrigo Luger's work showed. They may start out dry initially to start with, just no water at all. Depending on where they form, the planets in their habitable zones could be tidally locked, which has a number of effects, and I'm certainly not going to touch on that. And flares, as we've heard several times today, could have a very detrimental effect on a planet, even if it does have an ozone shield. But one of the things that Feng Tian and myself pointed out in 2014 and 2015 is that some of these planets could potentially build up oxygen in their atmospheres to the level where we might be able to see it and detect it as a false positive. So what do I mean by a false positive? If we look at the Earth's history, and particularly the evolution of the atmospheric oxygen budget on the Earth, the Archean is noted to have very low oxygen, and then at the GOE, you see a rise of oxygen to between 1 and 10% classically. This estimate has been revised downward from some of Noah Planovsky's work, so at most it might be 0.1% of the present atmospheric level of oxygen, which is not a lot of oxygen. And if you think about this from a detection perspective, and this is again broad brushstrokes, I'm sure we're going to hear more about this likely from Sarah Rugheimer. If you look at this from broad brushstrokes, you can detect oxygen if it's greater than about 1% of modern oxygen. And you can detect ozone for about 0.1% of modern oxygen levels. And that's from a 2003 paper from Antigona Segura. Now, that means that there could potentially be vast portions of Earth's geologic history where we might not see life, but there could be life happening on the surface of that planet, as mentioned earlier by Nikki. And the corollary here is that a false positive could be any amount of oxygen that exceeds the amount of oxygen we expected for Earth's history where oxygen was a factor. So how are we applying this to Proxima Centauri b? I want to point out first that with any modeling effort, it is important to state explicitly what your underlying assumptions are for that model. Now, for our model, we're considering global redox balance as one of the gold standards for the self-consistent steady state of an atmospheric composition. And global redox balance is essentially the balance between reducing power coming into the atmosphere either through volcanic gases being introduced in the atmosphere or oxidative weathering. So that's a sink for oxygen or a net source for hydrogen, essentially, balanced by the escape of hydrogen to space and the burial of reducing constituents. Now, because my planet is lifeless, a lot of these things go away, which makes global redox balance a much easier equation to solve. And for us, global redox balance is satisfied when we balance volcanic outgassing by the escape of hydrogen to space. You can certainly make very different assumptions about your planet. For example, you can choose not to satisfy global redox balance, but you must state explicitly that you are doing so. It has a very different effect on your model results. So stating it explicitly is an important step. And what this looks like from a schematic level, at least for M-star planets, well, let me back up. It looks like this for most terrestrial planets, but it looks very different in application for M-star planets, is in the upper part of the atmosphere you can photolyze CO2 and you can make CO and O2 in stoichiometric quantities. And then that CO and O2 can flow into the lower atmosphere where water vapor photolysis catalyzes the recombination of CO and O back into CO2. And part of the 2015 paper, we outlined that this process is fairly slow around M dwarfs, and so one of the big questions is what happens to the CO and the O2 in this solution, in the ocean, global ocean. And they could potentially recombine, but those aqueous reaction rates are relatively unknown. So that's why there's a big question mark down here. And so I mentioned before that this catalysis is relatively slow in M-dwarf planets. And that's a relic of the fact that the spectra that you're seeing at the top of the atmosphere is very different for solar-type stars as compared to M-dwarf stars. Here you can see that a Sun-like star it's very bright in the near UV, and it's fairly dim in the FUV, but for M stars, particularly Proxima Centauri, it's essentially flat across the UV, which gives it a very high FUV to NUV ratio. And I zoomed in here just a little bit so that you can see, and these are 1 AU equivalent, so these are integrated to be 1360 watts per meter squared at the top of the atmosphere. That's why you're seeing relatively low contributions of UV and visible radiation from Proxima Centauri. It's mostly in the infrared where you're getting most of that radiation. But you can see that because it's relatively flat and it's a very different character FUV to NUV ratio, which affects the chemistry because a lot of the photolysis of important constituents in the atmosphere like CO2 and O2 and water vapor happen in a relatively narrow UV region. So how does it all fit together? The 2015 paper pointed out that the FUV to NUV ratio was the dominant control for the abiotic production of oxygen in a terrestrial planetary atmosphere. So these are 5% CO2 cases located at about 1.3 AU equivalent, so they're relatively far out in the habitable zone, relatively colder. And that decrease in radiation allows essentially the buildup of CO2 because we assume that there's a carbonate-silicate feedback cycle. But as you see for a Sun-like star, you get relatively low levels of abiotic oxygen, vanishingly small, what we think is commensurate with what we see in the Archean. But as you change the FUV to NUV ratio, especially for K dwarfs and M dwarfs, you see that the amount of oxygen you produce from CO2 photolysis is actually on the order of a few percent in some cases. And the new result here is that Proxima Centauri plots off the plot, which is never encouraging. And so you get up to about 15% oxygen from a CO2-dominated atmosphere in this case. And this is a very limited part of parameter space. If you include more CO2, you get more oxygen. It's just a consequence of the fact that you're photolysing CO2. But if you have less CO2, you will see less oxygen. That's this bottom panel here, where we varied the amount of CO2 in the atmosphere and watched as the oxygen scaled with it. And so I've put this dashed line here, which is my threshold for a false positive oxygen signal. And you can see that for large amounts of CO2, which is commensurate with being located in the outer regions of the habitable zone, it's entirely possible that you could build up some oxygen above that threshold. But for relatively small amounts of CO2, that oxygen false positive does go away. And you can include the effect of other reducing gases like more hydrogen, methane, ammonia outgassing, for example, which is not really a thing on Earth, but it could be on other planets. Composition is a thing. It actually decreases the amount of oxygen you can accumulate in the atmosphere. But because these planets are weird, and it's never easy, the likelihood of CO runaway, which is a consequence of some of the modeling we've done, has been outlined by Kevin Zonley in the past. The CO runaway becomes a more problematic issue. It occurs more often, especially when you introduce more complex chemistry in these cases. And so what I want you to take away from this talk is that with the same volcanic outgassing and boundary conditions, Proxima Centauri b behaves much like the other M-star planets in that it can accumulate oxygen potentially above this threshold that we've assumed for a false positive from Earth's history. But what you should note is that it also is dependent on the UV spectrum of the host star. So for F and G and K stars, they don't really show the same sort of behavior. So for much of the planets that we may observe in the far future, it's entirely likely that this mechanism is not going to be a large source of uncertainty in the amount of oxygen we might detect. And this result also is fairly dependent on which modeling group has contributed these results. And so we are currently well underway in a model intercomparison to try to root out exactly what's driving the differences between whether or not you generate abiotic oxygen. And so with that, I'd like to take questions.
All right. Thank you, Sunny. We have time for two, 3 questions here. We are on time. Our speakers are awesome. Go
The
ahead.
microphone. I was precisely on time, thank you.
Go, thanks.
Vladimir Arpichin, NASA Goddard Space Flight Center. So here you discussed the effect of the far UV and the near UV photochemistry on
Right.
those atmospheres. We find that the effect of XUV, EUV, and X-ray are much more important, especially when it comes to photoionization, because the process that you described is only works when everything is neutral and nice. However, it's not the case. And we found, and I don't know, you did mention our paper, when we discussed the Proxima B, the atmospheric loss escape due to the ion escape mechanism, which we find very, very important, especially when you have a high high fluxes, the energy fluxes in EUV, which is basically the case for a lot of M dwarfs, with
Right.
with exception of probably a couple of very, very weakly. That's one thing. The second is magnetic field. We know that the Proxima Centauri has a magnetic field 300 times stronger than our sun. So that means that at the distance of 0.05, the magnetic field, the BZ component, will be comparable to the magnetic field of Earth. We will destroy the magnetic field. So the magnetospheric effect become extremely important, if not defining, in the whole climate models, where under the assumption that everything is nice and soft. So that will change the whole dynamics.
I totally agree with your opinion about the X-ray being a large component of that, and magnetic fields are very important, but we do have some evidence that there are M-star planets, like the TRAPPIST system, that are compatible with being a few percent water, and if you've completely destroyed your atmosphere by drag-off, then where's the water component? So it seems like there's a disconnect there between what we're just seeing in nature and what we're modeling, which is, I agree, a big issue for us.
We'll have to go back to the next question. If maybe we can continue.
On Friday, I'm going to show some of the results of simulations for TRAPPIST.
Yeah,
Right.
after this.
A much shorter question. Your FUV, is it dominated by Lyman alpha?
Absolutely.
And then in that case, the cross sections of different molecules will be different, right?
So yes, that's also a disconnect, is because we're assuming that it's an average absorption across a wave band. So that is something that we can do better in the future.
And it is also pressure dependent.
Yes.
Yeah.
Yeah. So.
Okay, we have no more questions. All right, so we'll go to the next speaker.
Thank you,
Thanks,
Ravi.
Sunny, again.